So there's been a little request for some help on the problems. Here's a couple of solutions to the worksheets that we've used on acids and bases. So I'm going to start from the beginning and naming, identifying them. First off, you can look at a compound like this. This is the first worksheet we had from Wednesday. And you'll say, oh, it's got an H in it, so that's got to be an acid. And it's got two elements in it, so it's going to be hydro something, the name of the negative ion. So anyone with 2 is going to be hydro, chloric, and chlorine, drop the ene and put ic, acid. Okay? Great, that's an acid. It's hydrochloric acid because 2 elements. If it's a base, you don't worry about changing the name. It's just the name like we did for the ionic compounds, sodium hydroxide. So this is a base. It's got an OH group. That's what makes it a base. And that is sodium hydroxide. Okay, this has neither H as the front part, even though NH4 is part of it. NH4 is the polyatomic ion, so we think of it like a group. And the sulfate is not OH, so that's a salt. And that's just ammonium, polyatomic ion ammonium plus sulfate. For me, I write down those polyatomic ions, the simplest ones I had in the notes on a 3x5 card, and I worked to memorize those because those are the ones you see the most often as we're working through this. It'll make the exercises easier. Salt and ammonium sulfate. So you just look for the H's. Here's an acid. That one's got an OH in it. That's a base. Salt. There's an acid. So that's all we're looking for in these in this first sheet. Okay. Now let's continue down through. Let's see. Here we go. In the naming section, I got a little more systematic. Here you're going to notice most of these either have one element with a hydrogen or it's a polyatomic ion. If it's a polyatomic ion, it's easy. You just look up the name of the polyatomic ion. NO3 is nitrate. 8 compounds go to ic acid. So instead of nitrate, it's going to become nitric acid. And that's because the polyatomic ion was named nitrate. This becomes nitric. Okay, something like number 4 here is called it's just called bromite. BrO3 is bromite. I'm sorry, I'm 4. BrO2 is bromite. Okay, let me write that. The polyatomic ion here is bromite. Ite acids go to us. Sorry, ite polyatomic ions go to us acids. So this is going to become bromus acid. Sorry, that's a U there. So that's the way you're going to change these. If it's got an ite ending polyatomic ion, it goes to us acids. If it's got 8, it goes to ic acids. Now, when you come back to these ones like this, number 6, that's 2 elements. Now you got to go back to the naming for 2 elements. Hydrogen with other element instead of a polyatomic ion. Well, telluride is the name. Oopsie. Tellurium, sorry. I'm losing my mind here. Tellurium is the name of the acid, or not the acid, but the element. So this is going to become hydro because it's the 2-element system. Hydro, telluride, or telluric acid. Okay? So that's the naming systems. Anytime you see hydro, you think, oh, that's 2 elements. I'm going to go down here where it's got the name. So hydrofluoric is just going to be H with 1 element, F. That's where those come in. Whereas phosphorus, it doesn't have the word hydrogen in front, hydro in front, so I would think, oh, phosphorus is coming from phosphite. Us comes from ite. So it's going to be hydrogen phosphite. 2. And it's got a +3 charge, so if you remember, this is a -3, this is a +1, then that's going to be H3PO2. So that's some of the naming systems. I think that's pretty straightforward. The type of reactions that happen, I think you can find in these that the H being given up to the other substance is what makes something an acid, giving an H. So this is going to become nitrate without the H, and then you're going to have H3O which accepts the extra H. It just becomes an oxygen with an extra H. It's the H3O, or hydronium ion is what it's called. It's basically water dissolving a hydrogen, just like water dissolves these other ones. I left one here. If I go to Bronsted base, that means that this substance is going to pull a hydrogen from someplace. So I'll take nitrite, for instance, NO2, and it's going to pull one hydrogen from water, and this is going to then become OH minus. Oh, this doesn't have a charge, so come on. There we go. Again, one H got pulled, so that would be all still ones. Only one H get transferred, so that's all ones. Here would be an example where carbonate could pull two hydrogens, so if I wanted, I could say hydrogen 2CO3 plus two OHs, and that would make me have to have two waters that go there. So if I get both the H's onto carbonate, if I pull two H's, then I'm going to have two waters that have two hydroxides that are made. Single replacement, any metal that's higher than hydrogen on the single replacement reaction, the type of reactions was last week, single replacement, if Fe and H are compared, okay, whichever one's higher gets the partner. So here H is lower than iron, iron is higher, so it gets a partner. In this case, magnesium is higher than hydrogen, calcium is higher than hydrogen, so all of these do react. All these are both going to be the same kinds of reactions. So this magnesium is going to get a partner of sulfate, and the hydrogen gets the boot as a gas. You don't have to put the G in there, but that's, bubbles off. Double replacement, these are going to have, the outsides are going to react together and the insides are going to react together. The metal takes a new partner. So calcium is going to repartner with acetate, C2H3O2. Now, this is a +2 and this is a -1, so I need two of those. 2 minus 1s equals the 1 calcium plus 2 in terms of charge. You're always trying to get the charge the same, and then H and OH get together to make water. But since there's 2 here, I'm going to have two H's over on, sorry, 2 OH's there. I'm going to need to have 2 HOH's on this side. That gives me 2 H's here, so I'm going to have a 2 in this area. And then they end up balancing because I have 2 acetates. Now that was tricky, and I left an extra video with a gal that was teaching those, and she has another method that uses them. If you're still getting this balancing stuff down, take a look at that one from Monday's lecture. Okay, let's go on to conjugate acids. Notice if this is saying, what's the starting material that acts like an acid? Acid gives up H, so if I look over here, the thing that gives up H is HCO3. So here's the reactants in the starting material that act like an acid. The starting material is here. This is giving an H to this to become water and sodium. Okay, this one's giving an H, this one's giving the H that way. So here's the one that's the acid. Okay, that is giving the H over here to OH to become water. So this one is the acid. Now, so let's go and underline the conjugate to these things. The conjugate to this is just different, the compound different by a single H. That's the different one. Here's the one that's less by 1 H. Here's the conjugate to NH3. Cool? I think the ones on the bottom are pretty straightforward because they're very similar. It's going to go through the process. You identify the base in here and underline the conjugate to it, which is an acid. Which of the following substance can give an H and take an H? Anything that's still got room here is going to have a charge, typically, like CO3, but it's going to have at least one charge. So this can give H's, but it cannot take H's. In other words, it's full. It doesn't have room for extras. But this has room if it's got a charge for another H. So this can give an H because it's got an H in it, and it's got room with a -1 for another H. Same thing with this one. This one can only take H's. That one can only give H's. This one can only take because it's got room for them, but it doesn't have an H to give up. So it doesn't act like it has H's to give, but it can take them. Water can give and take H's. And then ammonia can give or take H's, and that's it. So those are the substances that can both give an acid because they have an H on them, and they can take an H. Molarity. This is the one that you guys probably were asking about questions. So first of all, we got a new symbol for what concentration is. Concentrations are given in square brackets of whatever's inside. That means what's the molarity of what's inside the bracket. 4 moles of sodium hydroxide in 3 liters, that's molar. That's what we've been using for concentration. 4 moles per 3 liters, or this is 4/3, which ends up being 1.33 moles per liter, which we give as a capital M. Okay, so you just take the number of moles divided in number of liters. Let's go down to one that's a little more tricky, number 3. I have 3 moles of H2SO4, and I am asking for the molarity of the hydrogen. So if I have 3 H2SO4s, when this goes into solution, we've already seen how we break things up that go into solution. The H's are going to come off as separate H pluses, and the sulfate's going to go in. So you're going to actually have 3 groups of 2 H pluses. That is really 6 moles of H. And it's in 1.5 liters. You have to put these in liters of water. So 6 over 1.5 ends up being 4 molar. Okay? So that's how you get that concentration. As we come down to the bottom, I'm going to start to help you see this chart. Really, it's I don't know, detailed, or it's a lot of work. But you should see that there's a pattern here. Okay? If I have 10 to the 0 moles, notice this has 14. The difference between those is that when you multiply those together, you get 10 to the 14th. Same thing as if you look at the exponents. That's what the P stands for. The P is the exponent, or the power on the hydrogen's concentration. The power on the OH concentration. They became 0 because the exponent is 0 on there, so its pH is 0. Here the pH is 14 because in the concentration of the OH, it's 10 to the minus 14th. Oh, these are all, I forgot those were minus 14s. I apologize. There's a couple there that didn't get a minus sign in here. I changed them on the answer sheet, but I don't know if I've changed them on the download sheet, so I apologize. Anyway, if this is going to be 10 to the 0, 10 to the 1, notice I'm just getting 10 times more concentrated, or more dilute each time. So this is going to be, if this is, for instance, 10 to the 1st, this has to add up to 14. The exponents do, so this is 10 to the 13th. Minus, this is 10 to the minus 2, this has to be 10 to the minus 12. And notice I'm just working my way down. 10 to the minus 13, 12, 11, 10, 9, 8, 7. So this is 10 to the minus 10th. And you'll notice that's 10 to the minus 4th. Again, the multiplication of those two ends up being 10 to the minus 14th. And the pH and POH add up to 14. So this is 1 and 13, 2 and 12, 3 and 11, 4 and 10, 5 and 9, 6 and 8. Here I just give you these so you can look at the 7s and 7s. Okay, and so on and so forth. So that's how those pH and POH are related. pH, POH add up to 14, whereas the exponents, when you have them in 10 to the form, it's multiplied together to make 10 to the minus 14th. So that's where you get down to here. What's the POH of a 1 molar solution? Well, 1 is just 10 to the 0 power molar. What power do you raise 10 to get to 1? 10 to the 0 is 1. So what's the POH? This is the molarity of the OH. Sorry, let's clean that up just a bit. 0 is the POH. It's what's the power of the OH concentration. That's what P stands for. Okay, 0.1 molar. Well, 10 to what power is 0.1? Or you can think of how many places do I have to move the decimal to get it behind that first number. I have to move it 1 more over because it's 10 to the minus 1 is 0.1. So if that's the case, 10 to the minus 1 molar hydrogen. The exponent on 10, the power on 10 is minus 1, so you got to take the opposite of it because the pH is the minus log of the hydrogen concentration. Let's take something like, I don't remember this off the top of my head, but it's on the answer sheet. So I'm gonna stick with these easy ones just so you can see them, and then if you have your calculator, you just got to take the minus log of 0.48. I think it's 3.6. I think it's 3.6. And that's just what I remember. All right, let's go down here. How many places do I move the decimal to get behind the first number for this? This is 10 to the minus 1, minus 2, minus 3, minus 4, minus 5. So this number is really just 10 to the minus 5th moles per liter of hydrogen. Okay? So what's the power on the concentration of hydrogen? 5. Well, it's the opposite of the power, so it's -5, but pH is minus log. Again, most of the time these concentrations are so small, so that's why they put the minus log, is because then they'd be positive numbers. You'd be dealing with positive numbers, and then whoever made that system thought that was easier for people to understand. Cool. Let's go down to the bottom. So those are a series of those in terms of working them. Let's find some pH and pOH of these. These are the last ones where it's kind of no holds barred. I might give you the hydrogen concentration, ask for the pOH. Well, then you're going to have those relationships that are on the worksheet. As a matter of fact, this one doesn't have that relationships, which I did type onto the top of yours. If I know the hydrogen concentration, first of all, what's the concentration of the OH? Okay, that's 3 places over, so it's 10 to the minus 3. The OH is 10 to the minus 3 molar. That means the pOH is equal to 3, right? They add up to 3. The exponents are 3. So if 3 and what add up to 14, that'll give you your pH. That 3 and 11 add up to 14. So the pH of a 0.001 molar sodium hydroxide is actually, we see it here, is 11. You find the pH of an HCl solution. Oh, that's directly right there. What's the power of the molarity of H on this? It's whatever this exponent is, because I have an H solution. It tells me what the concentration is. The pH then is 4. I have a potassium hydroxide that's going to have a pH of 10. Now, this is telling you what the pH is, so I don't even have to do the calculation. Right there is the answer, 10. Oh, but it's not asking that. Sorry. Let me erase those. It's saying what's the hydrogen molarity, the concentration. This is the power on 10. It's the negative 10. 10 to the minus 10 is the molarity. Oh, for goodness sakes. 10 to the minus 10th. All right? You just take that's the power on 10 of the molarity of the hydrogen. And I already gave you the pH, so you just use it as the power of 10. I'll do one more. Let's go to the bottom here, because that should give you one that's got like 2 H's on it. Here we go. Find the pH. This is number 11. Find the pH of a 0.5 molar solution of calcium hydroxide. First of all, if it's 0.5 molar in hydroxide with a 2 in it, that's 1 molar in just the hydroxide part, because when this dissolves, 2 of those go into solution, so it's twice the strength of the calcium hydroxide, because there's 2 for every 1 of the calcium hydroxides that go in. So if it's 1 molar OH, the pH, what do you raise 10 to get to 1? 10 to the 0. So the pOH, I apologize, pOH is 0. That means the pH is whatever adds to this to equal 14, or the pH is 14. Cool? So that's how we work those solutions out. There's a relationship between pH and pOH. Acid-base neutralization, this is if it's 1 molar and you're in 1 liter of solution. 1 mole in 1 liter is 1 mole of hydrogen. And there should be 1 mole of chlorine, because when it breaks apart, the 2 separate into different ions. So you get 1 mole H, 1 mole Cl, and they're all surrounded by water. Let's go to something that's a little more tricky, not much. 1 mole per liter of H2SO4 has twice the concentration, because every mole of H2SO4 gives up 2 H's, so this doubles the concentration of H. On this side, you're going to have 1 mole of sulfate, because for every H2SO4 in, there's only 1 SO4. Okay, we'll go down a little bit to the bottom. Let's try this one with aluminum hydroxide. Half a mole of aluminum hydroxide is still going to have just per liter, half a mole per liter of aluminum hydroxide, still going to have half a mole per liter of aluminum. But you're going to have 3 times as much hydroxide. So that's 1.5. Well, it's already here, so I don't need to write it. 1.5 moles per liter of hydroxide. So if that's the case, we'll finish this. This is what most of the time what we have to do is when we get a strange acid, we want to know its strength, or the strange base, we know the strength. We'll mix it with an acid that you know the strength of, so you can find it. It's called neutralization or titration. This is as complicated as we get in terms of this. If we say how many moles are needed to neutralize some sodium hydroxide, how many moles of sodium hydroxide needed to neutralize 1 mole of HCl? Well, if you have 1 mole of HCl, that means you've got 1 mole of H, so I need 1 mole of OH. Okay? To get a feeling for how I'm going about that, what if I had sodium hydroxide and I had to neutralize 1 mole of H2SO4? That means I have 1 mole of H2SO4, but that's 2 moles of H. So I'm going to need 2 moles of sodium hydroxide to neutralize that. And for fear this is getting a really long video, hopefully you fast forwarded it to the parts you needed. Let's use this guy. How many ALOHs do I need for 1.5 mole of HCl? That means I have 1.5 moles of H. To get 1.5 moles of H, just like I did up here, I'm going to need a half a mole of ALOH. Because every ALOH gives up 3 hydroxides. Hopefully that's helpful for your problems, at least to see how those are set up and run, and I hope this video you've been able to fast forward to the parts that you needed.